So thank you, Julien. All right, so thank you very much for the invitation. I'm very glad to be here. I was not sure about the audience and the background of the audience, so I tried to make it accessible for everyone. I am a fluid mechanician. As you can see here, I do my research at the LEGI lab, so it's geophysical and industrial flows. I do my teaching activities here, so this amphitheater is the place where I teach essentially during the school year. I am also the holder of the chair OXALIA. I will say a few words about that. I slightly changed the topic, but I will talk about hydraulic structures, and I kind of narrowed down the scope. Just a few words about the chair. I don't know if you heard about industrial chair. They are run by the Fondation Grenoble INP, so it's kind of mécénat, so a relationship between research labs and the Grenoble INP Foundation. And they give money, a company gives money to try to trigger research in their field of interest. So with OXALIA, we built this chair. With Artelia, we built this chair OXALIA, which doesn't mean anything. It's just name ALIA, which is very close from Artelia. And it's about multi-phase hydraulic flows. More specifically, there is three research themes. So this is in French, but I just translate the first one. Affouillement, which is scour, and I will define that, and it will be the topic of my talk today. The second topic is morphological evolution of coastal zones and rivers. And the third topic is the modeling of air-water mixtures, like in plunging jets and so on. So the topic of my talk today is scour around hydraulic structures, which in fact is the main cause for bridge failures. And I will show you statistics about this in a few minutes. This is the outline of my talk. A few motivations, analysis of the recent, not so recent, bridge failures in the US. Then I will describe the flow and sediment transport processes involved in this problem. I will say a few words about the numerical modeling that we try to do, both in engineering and in research, to solve this topic. I picked a case study from Artelia, so they gave me a recent case that they did on a bridge pile on the LGV Paris-Bordeaux, so it's the fast train line between Paris and Bordeaux. And I will conclude with the development of a new generation of numerical model, which is the topic of the chair. All right, motivations, two examples. So here is a movie of Okay. Cut it short. So it's just an illustration of what can scour cause. You see this build is completely destroyed, and it was in 2007 in the Réunion Island. This bridge crosses the Saint-Étienne River. And this is due to a cyclone, so it's very massive events, hydrological events. The main issue is that this bridge has been built in 1930. So it's about 24 years or 25 years of lifetime, which is not enough for a bridge. So we have to be careful when we build this kind of structure. When there is a pile in the riverbed, in the river, we need to protect them against this scour phenomenon. The second application or field in which this process is important, which is a very hot topic nowadays, is marine renewable energy, wind farms. When we build wind farms, we use jackets. So these are the jackets of the Saint-Brieuc wind farm in France. This is 30 meters high. Okay? You put that in the ocean. There is tidal currents. There is waves going on. So at the foot of those structures, the soil may be dug by the flow, and it may lead to the collapse of the structure. A wind farm is typically built for 50 years, so we need to account for these processes for a lifetime of about 50 years. So these are the motivations for this work. And if we look at the statistics of bridge failures in the US, so those two authors published a paper in 2003, so at this stage it was recent, so now it's not so recent, but at least we have all the statistics, so it's very interesting. The principal cause of failures are essentially external. Like here, there is about 500 bridge failure, collapse or distress. And among all the possible causes, 415 or 20 are due to external causes, okay? Like the engineers did not mess up with the design, they did not mess up with the construction or anything like that. The main cause is external. And if we focus on the external causes, they are classified here by the rank of importance, and the top ones are flood and scour. It's very hard to differentiate difference between flood and scour, but they represent about 50% of the bridge failure. So it's the main cause of bridge failure in the US. And just to tell you a few words about the number of bridges that are concerned by this problem, there is 700,000 bridges in the US in 2002. 500 failed during the period from 1989 to 2000, which makes the average lifetime of the collapsed bridges of about 52 years. Okay, it's clearly not enough. And 2,500 new bridges are built every year in the US. Okay, so it's a very hot topic in civil engineering to be able to predict and design protection for bridge piles. All right, so I just gave you the motivations and a few words about the statistics, but now let's look at what is scour and what happened to the flow when it goes around a hydraulic structure like a bridge pile. So this is a schematic taken from a research paper. So if you idealize the flow, you have a circular pile, like a bridge pile. You have a flat plate at the bottom, which is fixed and smooth if you are in a research lab most of the time. And you have an incoming flow here. The flow goes around the cylinder, and by doing so, generates various kinds of vortices. The first kind, which is very classical, and I will show you movies about that, you have lee-wake vortices, like the so-called von Karman streets, so the alternate vortices shaded by the obstacle. And if you go along the Isar River to the campus, if you end up close to a bridge, you will see these kind of vortices. They span over the entire water depth. The second kind, which you don't see most of the time, are the horseshoe vortex system near the bottom of the pile here. And again, I will show you snapshots of that. But here, basically, the flow hits the structure. You have high pressure here. The flow is forced to go downward. And when it reaches the junction with the bed, it rolls over itself and generates this kind of horseshoe-like. So it's because the shape has the shape of the horseshoe, which goes around the structure. And all those vortices generate high-speed flow velocities, which generates intense forces or bed shear stress on the bed particles, which lead to their transportation. And in the end, it's digging the bed around the structure. This is what we call the scour phenomenon. So here's a movie from the National Committee for Fluid Mechanics film. So if you are willing to learn a bit of fluid mechanics in a fun way, I really encourage you to visit this website. They have movies from the 60s, very vintage, but very nice. And the one I show you here is taken from Flow Instabilities by Professor Molo Christensen from MIT. I will just play a few minutes to show you how vortex streets are generated when a cylinder is experiencing a flow.
The cylinder is steady, although we can see a slight instability in the wake. Increasing the Reynolds number by increasing the velocity, the flow around the cylinder becomes unsteady. A vortex wake develops, the Kármán vortex stream.
Yeah.
Just below critical Reynolds number, the stability is precarious. A small accidental disturbance is enough to trigger large fluctuations.
There's a small shift between the audio and the video.
Look at that again.
Stable,
Steady,
perturbation.
stable flow, the bubble, and here it goes. Now we are in a larger cylinder. The Reynolds number is larger and above critical. The critical parameter is
Because the large cylinder is now.
It is this instability which makes telephone wires sing in the wind. As we have seen, a steady flow may become unsteady for certain ranges of flow parameters. The instability takes its energy from the mean flow, and the mechanism can be thought of as a selective amplifier, its characteristics governed by flow parameters. The cylinder is steady.
All right. So as Møller-Christensen told you, the control parameter for the flow around the cylinder is the Reynolds number. So in fluid mechanics, we like to talk about dimensionless numbers. This one is probably the most famous. It's a velocity time a length scale. So here is the pile diameter divided by the viscosity of water. If you look here, you have the whole range of flows around the cylinder going from very small Reynolds number, here is smaller than 5. Very low, it's what we call creeping flow. You have no recirculation, no vortices, nothing. It's like dragging a cylinder in honey, very slowly. But when you increase the Reynolds number, you see that the Kármán streets starts to develop. At the beginning, they are laminar. If you go to very large Reynolds numbers, you end up with a full turbulent wake. If you take the numbers of a bridge pile, which let's say the diameter is about 10 meters, and the velocity of the water is about 1 meter per second, you end up with a Reynolds number of 10 to the power 7, which is in this range of the classification. So everything is turbulent. The boundary layer is turbulent, the wake is turbulent, and we have to cope with that, which is a very challenging problem. Simulating turbulence in flows is still a challenge. All right, so these are for the Lie wake vortices. If we look at the horseshoe vortex system, so what's going on here, in these experiments, which are pretty old but still very interesting, they have a hydrogen bubble wire which generates very small bubbles that are tracers to the flow. Here you see the junction. The cylinder is here. You see the cylinder in a vertical slice, and this is the bed. Here you see a vortex, and this is for different times. This is a secondary vortex, primary vortex, secondary vortex, maybe another one here, another one here. So you have a whole bunch of vortices here that moves around. If you look at this in time, over a period of about 1.5 seconds, those vortices move in time. This is a schematic. So here the flow goes down, rolls over itself, generates a first vortex, a secondary vortex, and a third vortex. So this one would be this one. And if you look at it from the top, you see that it goes around the structure with the same shape as the cylinder. So these are views from the top, and you see here the shape of this vortex. Okay, so as I told you, once we have these vortices, they exert some forces on the bottom, and it transports sediments, and it's digging the bed. This is the scar hole that engineers need to prevent to avoid the failure of the structures. In the framework of the OXALIA chair, we did a small experiment that we presented in this amphitheater a couple, maybe 2 years ago, just to illustrate what is happening when we have a flow, incoming flow over a movable bed. We call this scar movie. So these particles are made of plastic, very light, so very easy to transport. This is a cylinder 2 centimeters in diameter, pretty small. And the flow is increasing gently in time. So at the beginning, you see these shaded vortices that will extract the particles from the bed and suspend them. And if you look in this region, you see the scar hole forming due to the vortex, horseshoe vortex system. This process is very fast. The movie is at speed 1. So just in a few minutes in the lab, you can completely remove the soil from the bed. So in order to solve this or predict this type of mechanism, we'd like to use numerical modeling. At least this is what I'm doing. And for that, if you do a bit of fluid mechanics, you probably know that we use Navier-Stokes equations. And in this case, as the flow is fully turbulent, we use a Reynolds averaging. Reynolds averaging is either time averaging or statistical averaging. It's not the point here. What it changes for the Navier-Stokes equation, that it adds an additional stress, which is due to turbulence. And we close that with turbulence models, which is clearly the weak point of the approach. And here I show you what we use in engineering, K epsilon or K omega SST models. Basically, we relate the eddy viscosity to the turbulent kinetic energy of the fluid and the turbulent energy dissipation. In the framework of the chair and in the framework of the Master 2 internship of Matthias Renaud, funded by the Chaire OXALIA, we decided to evaluate 2 different models, OpenFOAM and Telemac 3D, which solves this equation, the same equations, but with very slight differences. So I tried to summarize just very quickly the differences. They use different methods. OpenFOAM is using finite volume method, Telemac 3D finite element method, but it should not change anything to the solution. The main difference is that in terms of meshing strategies, OpenFOAM is using a fixed unstructured grid, while Telemac 3D is using what we call sigma coordinate. So it's a terrain following and free surface following coordinate system. And this model has been built for large-scale application. People in Artelia call it GFD, geophysical flow model. While OpenFOAM is really a computational fluid dynamics model, which is very well suited for fine-scale flow predictions. So the first thing we did is to try to simulate the flow around the cylinder, the same case for which we have data with the 2 models, to select the best candidate for the future of the model development. So at the top, you have an illustration of the OpenFOAM solution. What you see here is what we call a Q criterion. It's just a representation of the coherent structures, okay, vortices. So here, you see the horseshoe vortex that I talked about. These are the shaded vortices. See, they span over the entire water depth, like columnar vortices. With Telemac 3D, very similar patterns, but slightly different. You see there is not much variation near the bottom here. But, okay, in both cases, we do observe the vortices. The question is which one is the best? And to do that, we need to compare with experimental data for this configuration. So this is what I show here. The cylinder is here. Each plot represents a different elevation. 20 centimeters above the bed, which is about the water depth. 5 centimeters, 1 centimeter, 0.5 centimeters. So here we are very near the wall. The points are the experiments. The red profile is Telemac 3D, and the green one is OpenFOAM. Very far from the wall, you don't see much differences, except maybe in the wake. But as you reach near the bottom, here you see a very significant difference, especially in the horseshoe vortex region. The green one fits quite well with the data, while the red one, not at all. And as this is the driver of the scour process, we then select the open form, so the true computational fluid dynamics solver, for the purpose of the development of the future model. All right, so this was for the flow processes. Now I move to sediment transport. J'ai combien de temps pour savoir si je coupe des trucs ou pas?
Prends ton temps, we have time.
Okay. So sediment transport processes, the main parameter or the main feature that we need to understand, or that you need to understand, is the existence of a threshold of motion for particles deposited at the bed. If you take this sketch here, you have the bed. We take one isolated particle, and we make a force balance on it. The driving force is a drag force. Okay? So you have a flow above it, and we assume that this particle will be set into motion by a drag force, which is given by this very classical expression. And the stabilizing force will be a friction force. Okay? So the weight of the particle, W, times a friction coefficient, which can be seen as some kind of tangent of the angle of repose. So if this drag force exceeds the stabilizing force, the grain at the bottom starts to move. I write this down here. If in this equation we put on the left side all the dimensional parameters and on the right side all the dimensionless parameters, we build a non-dimensional parameter, which is a critical Shields number. So it's UF square, the near bed flow velocity, divided by the density ratio minus 1 times gravity times diameter. This is the criteria that we use to say if, for certain conditions, the particles are moving or not. Experiments done a century ago by Shields are gathered on this curve, and okay, as always, they are a function of the Reynolds number. But basically, what these curves tell you is that particles don't move for this number between 0.03 and 0.06. Okay. So when we do simulations and when we get the flow around the cylinder, if we plug this function or this criteria, we can determine when the particles move and when the particles don't move. If we exceed this threshold, the particles are moving, they are transported, and then we need to predict how much particles are transported for a given flow. So we have a whole range of regimes. The first one is bed load, when the particles are moving very near the bed with permanent or intermittent contact with the bed. So it's very near the threshold of motion. If we increase the Shields number more, the particles start to be picked up by the flow, by the turbulent vortices, and they are transported as suspension, as I showed you in the movie earlier on. And this is characterized by another number, which is a ratio of bed friction velocity to settling velocity. To make the long story short, if the turbulent velocity fluctuations are larger than the settling velocity of the particles can be picked up by the flow and transported in suspension. Otherwise, they settle to the bed and they are transported as bed load. In engineering models, this is the water column. We split the domain in two parts. In the suspended region, we solve hydrodynamic equations, Navier-Stokes, plus a transport equation for the concentration. And very near the bed, it's about the size of the particles, a few times the size of the particles. It's not resolved by the model. And we parameterize the bed load as a sediment flux. And the interactions between these two layers is parameterized through empirical formula. Okay, so it's a simplification of reality where we use this kind of parametrization for the pickup flux like that and the bed-out flux like that. Okay? So this is what engineers use nowadays to predict the morphological evolution of a natural system, such as a river, coast, or even a scar. In research, the most part of my research activities, as Mathieu told you this morning, is to put solid in fluids. Okay, I'm a fluid mechanic guy, so I'm more on the fluid side. But we'd like to develop new models that we call two-phase flow models, where we solve dynamical equations for both the sediments and the fluid. So it's a very physically based approach. So here, I told you we have empirical formula for almost everything. Here, we try to resolve the mechanical equations for the entire range of concentration, including in the immobile bed. So here we use rheological models, kinetic series, and so on. And in this approach, we can incorporate most of the dominant processes, like turbulence-particle interactions, and even particle-particle interactions. And we don't have to split the water column arbitrarily between what's going on in the bed and what's going on in the water column. The main difficulty is that a lot of those processes are very complex to model, and it took us about 20 to 30 years to get closures for all those processes. And the second problem is that it's very expensive, as I will show you in the next slide. So we cannot apply it to large scale, and it's not possible to use this approach in engineering applications. So using this, we did the first application of this type of model to study the scar around the cylinder. So here you will have a movie. This is a cylinder. Here is the bed in the two-phase flow model. So inside this layer, we solve mechanical equations by resolving the granular flow as a continuum medium. Here you will see the streamlines of the incoming flow colored by their velocities. The gray level is the bottom elevation taken by reference of its original position. All right, so you see the flow is going down, the horseshoe vortex, the necklace vortices. Here, the entanglement of the streamlines represents the vortices that are shed behind the cylinder. And you see that the bed is dug around the cylinder through what we call the scar process. Qualitatively, it's nice. Quantitatively, it's not too bad. Here I show in magenta a comparison with the experiments as red dots of the scar depth. So how much the bed has been dug upstream of the cylinder and downstream of the cylinder. Of course, the results are not perfect, but qualitatively, after 600 seconds, so about 10 minutes, the amount of sediment that has been taken out from near the cylinder is approximately correct. But this is really a proof of concept, and it's really the first time that this type of simulations was done with this approach. But as I told you, the CPU cost is very large. It ran for 2 months on 128 cores just to perform 10 minutes of simulations. So when I say that to artillery engineers, they tell me, okay, it's not possible. I cannot afford that. So you need to do something else. But it was the starting point of the OXALIA chair to discuss with them and come up with some kind of agreement in between this and their approach to improve the engineering practice. Engineering practice is the next slide. It's the state of the art. So the most basic approach is the 0D modeling. To prevent scar, what engineers do, it's this movie. You have a bridge pile here. They put riprap, like big boulders, and the question is how big these boulders should be to protect the bridge pile. So you remember I told you about this threshold of motion, this critical shield number. So this is the criteria that they use. But for that, so you can define a D50, which depends on the water depth and the flow velocity, and the density ratio of the boulders to determine how big these boulders should be to prevent the scour from developing. Here you see you need two informations. You need a velocity and a water depth. So you need a hydrodynamic model to get these informations, or a physical model, right? Physical model, this is an illustration of a physical model that Artelia did for a bridge in Bordeaux. The red particles are the same as the one I showed you in the movie of scour earlier on. But when you do physical models, you have two limitations. The first one is the scale issue. You reduce the scale, but you still use water. So you are not at the same Reynolds number. We are completely stuck with this Reynolds number. And you cannot change the fluid. So there are scale issues. And the cost to build this type of model is about a few tenths of kilo euros. So not everybody is ready to pay this much to study or prevent scour. The alternative is to use numerical modeling, essentially hydrodynamics, sometimes 2D, and nowadays more and more 3D models. So what do Artelia do when they are asked to analyze scour in a real case? So this is taken from a real study that they did. The initial design of the Dordogne viaduct. So Dordogne viaduct is here, okay. So this is the Gironde, Bordeaux is here. This is the true full-scale viaduct that has been built in 2017, so it's very recent. And the study was done in 2012. This is a picture taken from the physical model that they did at this point. You see that the pile, at the bottom there is a footing, which is above the bed, and they have designed scour protection with riprap on both sides of the pile. Okay, so this is what they suggested to do. They built the viaduct in 2017, and then they followed the bathymetry year after year. And in 2020, so only 3 years after the construction, they realized that the digging was too fast, and they reached the level of vigilance. So they had to go back and make a new study to evaluate why the bed was dug so fast and to propose remediation solutions. And for that, they used numerical models. The experts said, okay, the problem is that if you start digging the bed, the footing becomes too large. And then the problem is not the scar around the structure itself, but it's the scar around the footing. So Artelia did numerical simulations. Okay, so this is the sketch, and this is the mesh that they use. So you see it's very fine. Okay, so the computational free dynamic simulations that they do are very highly resolved. The cost is very large. And they did two situations. One at the physical model size with the original footing, and one with a larger footing, just to check if a larger footing could lead to an additional stress on the bed. And indeed, if you look here on this view, you see that this is the flow velocity. You see that the down jet that impinge the bed here seems to be stronger when you have a larger footing. In the numerical simulations, they can get the bed shear stress in this region, and they realize that at the field scale, the bed shear stress was 150 Newton per meter square here and 180 Newton per meter square in this raised footing configuration. So if you come up with the Shields curve that I showed you earlier, but for those parameters, the Shields number is about 0.046 to 0.055. I plot this as an orange rectangle here. So we are right in the stability limit. Okay, so maybe, in fact, the riprap that they placed was too small for the hydrodynamic conditions that are faced by this bridge pipe. So this tends to confirm the expert hypothesis. And now the question is, what do we do to solve this matter? Or what OXALIA is doing? They do this kind of approach. So I mentioned these two models, this large-scale Telemac model, Telemac 3D. All right. So they did a large-scale simulations of the Dordogne River, going from here to here. The viaduct is around there. So they make a zoom here. They take the data from the large-scale model, flow velocity, water depth. They looked at different scenarios, hydrologic scenarios. And in this region, which is pretty far from the estuary, but still you have the influence of the tide and of the river discharge. So they did 3 configurations. I'm not going to detail all that. But from those simulations, they can force a small-scale model for the near field using OpenFOAM, so the computational fluid dynamics model. So this is a snapshot of the OpenFOAM simulation with a true bathymetry that has been measured in 2020. And you see the scar mark near the footing here, which is the problem for the decision makers. And they did these different simulations. I just show you one snapshot. So this is the bridge pile. These are the transect. So this one is here. And you see here on the velocity field that, okay, as in the previous simulations, we do observe an impinging jet, which is pretty strong, at the footing, near the footing of the bridge protection. And when they got the bed shear stress here, they realized that the riprap was too small. The recommendation is to refill the riprap, but with a larger particle to increase the intrinsic stability of the protection. And they advise to use 40 centimeter, which makes the Shields number to be 0.023 at worst, and which should maintain the protection for the strongest conditions faced by the bridge pipe. So this study shows you how we can use 3D numerical simulations at different scales, okay, to evaluate the scar problem and to propose remediation solutions. So at least this is what engineers do nowadays. But the main limitation so far is that, okay, they just did hydrodynamic simulations. They did not did any sediment transport or bed evolution simulations. And this is the goal of the Chaire, to develop a new model that is able to predict the scar, so the digging of the bed, with reasonable computational time so that engineers can actually use it in practice. So this is the topic of Matthias Renaud's PhD thesis, which started in 2022. We do open source modeling. Okay, so we couple Navier-Stokes simulations with transport equation for the concentration and a bed evolution equation. And this is just the first result of Matthias. Here you have like a sluice gate, a fixed bottom and a movable bottom. So here you have a bottom jet that is going from a non-movable bed to a movable bed. It generates another form of scar. So here is the scar mark, and you generate, as you extract some particles here, mass is conserved, and you generate a dune downstream. And if you compare qualitatively with experiments in the same configuration, the shape of the deposit is the same. So the model is pretty convincing, but the next step will be to apply this type of model to the field scale problem to try to solve actual engineering problems. All right, so I reached to my conclusion. Scar is one of the main risks for hydraulic structure collapse, at least from a fluid mechanics perspective. 50% of bridge failure in the US. The current structures and the vortices are responsible for the digging around the structure. Scar protection, such as riprap, are estimated using empirical formula, but we need detailed hydrodynamic information that are obtained from physical and numerical models. So engineers need to have the skills to be able to predict the flow conditions around the structure. And the goal of the OXALIA chair is to develop a new generation of model capable of solving this issue. With that, I conclude my presentation, and I thank you very much.